Hello, my dear dreamers, and welcome back to Hafee Sleep. Whether you're curling up for the night, taking a moment of peace in the middle of your day, or just letting your mind wander to far-off places, I'm so incredibly glad you're here. Before we drift into today's cosmic journey, I have a small, warm request. If the stories we explore together in this quiet space bring you comfort or a moment of wonder, please consider supporting our little community. Hitting that subscribe button is like leaving a nightlight on for us. It helps you easily find your way back for more stories. And if you press like, it's like a gentle wave back, telling me which journeys you enjoy the most. I often lie awake wondering where in the world you all are, listening along. So, if you feel like it, I'd love for you to leave a comment below and tell me two things: where you are right now and what time it is for you. It's always so magical to picture all of us, scattered across the globe in different time zones, sharing this one peaceful moment together. Now, let's dim the lights, get comfortable, and let our thoughts expand outwards, beyond the confines of our rooms, to explore one of the universe's most beautiful and absolute rules: why nothing, not even our fastest dreams, can ever outrun a beam of light. Imagine you're a kid in a cosmic car, your foot pressed flat to the floor on an infinite empty highway. The engine roars, the scenery blurs into streaks of color, and the speedometer needle swings further and further around the dial. 100 kilometers an hour, 1,000, 1,000,000. You feel the incredible thrilling rush of acceleration. You push it further, aiming for the ultimate speed limit, the universe's own top gear, the speed of light. You watch that needle climb, expecting to blow right past that final famous number. But then something bizarre happens. The harder you press the pedal, the more the universe itself pushes back. The engine is screaming, pouring out unimaginable power, but your speed isn't increasing nearly as much as it should. You're putting in exponential amounts of energy for the tiniest of gains. And then you notice something even stranger. The world ahead of you is compressing, squeezing itself into a tunnel of light. The stars to your side are changing color. And your own body, your own car, begin to feel impossibly, infinitely heavy. You are not slowing down. You are hitting a wall. A wall not of brick or steel, but of space-time itself. The universe, it seems, has a strict speed limit, enforced not by cosmic police, but by the very fabric of reality. And that limit is 299,792,458 meters per second. The speed of light. And nothing, absolutely nothing, can go faster. Now you might be wondering, why? Who made this rule? And why is it so utterly unbreakable? Well, buckle up. To understand this, we need to take a little journey, not just through space, but through time, through thought, and through one of the most beautiful and mind-bending ideas ever conceived by humanity. Our story doesn't start with complex mathematics or giant particle accelerators. It starts with a much simpler question: what is light? For most of human history, it was a profound mystery. The ancient Greeks had their ideas. Some, like Plato, thought we shot little beams from our eyes to see things. Others had more nuanced, but still incorrect notions. The real scientific investigation into light began in earnest with Sir Isaac Newton in the 17th century. Now, to really understand why a genius of his stature would latch on to this idea, we have to step into his world for a moment. The 17th century was a time of immense change. The scientific revolution was in full swing, but it was still wrestling with ancient ideas. The world was seen by many as a grand, complex machine, and Newton was perhaps the greatest mechanic the world has ever known. He looked at the planets and saw them as balls moving through space, governed by the precise, predictable laws of motion and gravity. He looked at light and tried to apply the same mechanical philosophy. What could be more mechanical, more satisfyingly straightforward than a stream of tiny, perfect particles? Imagine him in his study, a beam of sunlight cutting through the dust motes in the air. He takes a glass prism, a simple triangular piece of glass, and he places it in that beam. And magic happens. Well, not magic, science. But it must have felt like magic. That pure white sunlight, upon passing through the prism, explodes into a vibrant ribbon of color: red, orange, yellow, green, blue, indigo, violet, the entire spectrum of the rainbow. This was a known parlor trick at the time, but Newton investigated it with a rigor no one had before. He called it his experimentum crucis, his crucial experiment. He reasoned that if light were a wave, as some of his contemporaries were beginning to murmur, this colorful display might be explained by the wave being somehow corrupted or modified by the glass. But his particle theory offered a beautifully simple explanation. He proposed that white light wasn't pure and fundamental at all. Instead, it was a chaotic mixture of all the different colors, and each color of light was made of its own unique type of corpuscle. Red light was made of red corpuscles, blue light of blue corpuscles, and so on. Now, here's the clever part. He suggested that these different colored corpuscles had slightly different properties, specifically different masses or sizes. When this mixed crowd of particles slammed into the glass prism, the glass would affect them differently. The red corpuscles, perhaps being heftier, would be bent or refracted less by the glass. The violet ones, lighter and nimbler, would be bent more sharply. The prism then was like a customs official at a border, sorting the chaotic crowd of particles into an orderly line based on their passports, their color. This sorting produced the spectrum. It was an elegant, mechanical, and utterly compelling explanation. This particle theory could also effortlessly explain reflection. Why does light bounce off a mirror at the same angle it came in at? Well, of course, it's just like a perfect elastic ball bouncing off a hard floor. There's no mystery there. The mathematics of it was clean and fit perfectly with his laws of motion. For Newton, this was the clincher. The world made sense when things were particulate, solid, and mechanical. The idea of light as a wave, rippling through some invisible, intangible substance, felt messy, unnecessary, and frankly, a bit mystical to his pragmatic mind. And let's not forget the weight of Newton's reputation. He was more than just a scientist. He was a titan. His work on gravity and motion had given him an almost godlike status in the intellectual world. When Isaac Newton spoke, people listened. And if he said light was made of particles, then by golly, it was made of particles. For the better part of a century, this was the prevailing view. Science marched forward under the assumption that light was a hail of tiny bullets. But science, like a good mystery novel, always has a twist. And the twist in this story came from a brilliant and somewhat underappreciated contemporary of Newton's, a Dutchman named Christian Huygens. Huygens was a polymath, an astronomer who discovered Saturn's rings, an inventor who made the first pendulum clock, and a superb theoretical physicist. And he looked at the same phenomena as Newton and saw something entirely different. Huygens wasn't convinced by the corpuscle idea. He pointed out a few problems. One was a phenomenon known as diffraction. If you shine light through a very narrow slit, The beam doesn't just create a sharp, clean line of light on the other side, as you might expect if it were a stream of particles. Instead, it spreads out. It bleeds into the shadowy areas. You get a fuzzy pattern of light and dark bands. Now try to explain that with Newton's particles. Why would some particles, after passing straight through the slit, suddenly decide to veer off to the side into the darkness? It didn't make mechanical sense, but to Huygens, it made perfect sense if light was a wave. Think of water waves again. Imagine a wide ocean wave approaching a narrow gap in a breakwater. When it passes through the gap itself acts like a new point of disturbance. The wave doesn't just emerge as a straight beam of water. It ripples outwards from the gap in a semicircular pattern. It spreads. It diffracts. Huygens saw this same behavior in light and thought, aha, this is the signature of a wave. He formulated a powerful principle now known as Huygens' principle. It says that every single point on a wavefront can be thought of as a brand new source of tiny spherical wavelets. The overall wave that we see is just the sum of all these billions of tiny wavelets propagating forward. This principle naturally explains diffraction. The edge of the slit becomes a new source of these wavelets, which spread out into the shadow region. It was a powerful alternative model. But Huygens faced a huge, and I mean huge, problem. Waves need a medium, something to wave in. Sound can't travel through a vacuum. It needs air. You can yell all you want in space and no one will hear a thing. Water waves need water. So if light is a wave, what is its medium? It clearly travels through the vacuum of space from the sun to the earth. What is rippling out there? Huygens, like others before him, proposed the existence of a luminiferous ether. This ether was imagined as an invisible, weightless, completely frictionless substance that filled all of space and all of matter. It was the stage upon which the drama of light played out. It had to be incredibly rigid to support the extremely high frequency of light waves, yet so ethereal that planets could whip through it for billions of years without slowing down a bit. It was a paradoxical substance, but it was a necessary one to save the wave theory. Now, imagine the scientific debate. On one side, you have Newton, the undisputed champion, with his simple mechanical particles that required no weird, invisible ether. His theory explained reflection and refraction with beautiful clarity. On the other side, you have Huygens with his waves, which could explain diffraction, but relied on this mysterious, undetectable ether that seemed to have impossible properties. It's no wonder that Newton's view won the day. The particle theory of light reigned supreme for over 100 years. The wave theory was a footnote, a curious idea that couldn't compete with the overwhelming force of Newton's legacy. The tide began to turn, slowly at first, in the early 1800s. The man who really truly turned it was an English physician and polymath named Thomas Young. Young was one of those fascinating characters who knew everything about everything. He contributed to deciphering the Rosetta Stone. He studied the physics of the human eye, and he was a master of languages. And he was about to perform an experiment so simple, yet so devastatingly effective, that it would shake the very foundations of Newton's particle empire. It's called the double-slit experiment, and it is, in my opinion, one of the most beautiful and profound experiments ever conceived. Young's setup was brilliantly straightforward. He had a light source. In front of it, he placed a screen with a single, very thin slit cut into it. The purpose of this first slit was to create a clean, coherent source of light, a single wavefront. Then, after that screen, he placed another one with two very closely spaced, parallel slits. Finally, behind that, he placed a viewing screen. Now, let's think about what should happen according to Newton's particle theory. Light is a stream of corpuscles. They stream through the first slit. Then they reach the two slits. Some particles should go through the left slit, some through the right slit. They should then travel in straight lines and hit the back screen. You would expect to see two bright bands on the screen directly opposite the two slits, a pile of particles behind the left slit and a pile behind the right slit. But that is not what Thomas Young saw, not at all. What he saw was a pattern, a beautiful, intricate pattern of multiple bright bands separated by bands of darkness. It was an interference pattern. This is the absolute, unmistakable calling card of a wave. Let's break down why. Imagine you have a calm pond of water. You take two sticks and you start jabbing them into the water rhythmically, right next to each other. Each stick is creating a set of circular waves. These waves now spread out and overlap with each other. Where two wave peaks meet, they combine to make a super big peak. Where two wave troughs meet, they make a super deep trough. This is called constructive interference. They build each other up. But here's the crucial part. Where a peak from one wave meets a trough from the other, they cancel each other out. The water becomes flat. This is destructive interference. Young's double-slit experiment showed this exact behavior for light. The two slits acted as two new sources of waves, just as Huygens had predicted. The light waves, spreading out from each slit, interfered with each other. On the viewing screen, the bright bands were where peaks met peaks, or troughs met troughs. Constructive interference. The dark bands were where peaks from one slit met troughs from the other. Perfect cancellation, destructive interference. There was no way, no possible way for a stream of independent particles to explain this. How could particles cancel each other out? How could two particles coming together create darkness? It was absurd. The only logical conclusion was that light must be a wave. It must exhibit this wave-like behavior of interference. Young's work was initially mocked and rejected. Attacking Newton's theory was scientific heresy, but evidence is a stubborn thing. Slowly, painstakingly, other experiments confirmed his results. The wave theory gained momentum. Augustin Jean Fresnel in France provided a robust mathematical framework for Huygens's principle, turning it from a neat idea into a powerful predictive tool. They could now calculate exactly what these interference patterns should look like, and reality matched the math perfectly. The final nail in the coffin for the pure particle theory came with the measurement of the speed of light in different materials. Remember Newton's explanation for the prism? He said different colored particles were refracted by different amounts. But the wave theory made a specific and strange prediction. It said that if light was a wave, then it must travel slower in a dense medium, like water or glass, than it does in air or a vacuum. Wait, slower? Wouldn't it go faster? Think of a particle. If you shoot a bullet into water, it slows down due to drag. So a particle theory might also predict a slowdown. But here was the twist. The wave theory could precisely predict how much it would slow down based on the properties of the material, and this prediction was linked to the angle of refraction. When scientists finally developed techniques to measure the speed of light in water, the result was unambiguous and shocking for the Newtonians. Light traveled slower in water, and the amount it slowed down was exactly what the wave theory predicted. The particle theory, which had argued that light particles would speed up in a denser medium due to stronger gravitational or other forces, was completely wrong. This was the knockout punch. So by the mid-1800s, the debate was over. Newton, the Titan, had been dethroned. Light was a wave. It was settled science. Of course, the pesky problem of the ether remained. What was this mysterious substance? But the evidence for wave-like behavior was so overwhelming that physicists were willing to accept the ether as a necessary, if awkward, part of the package. They set about trying to find it, to detect this invisible ocean in which we were all supposedly swimming. And this sets the stage for the next part of our story, the one we touched on earlier. The Michelson-Morley experiment and the great ether hunt that would ultimately lead to a young patent clerk in Switzerland having a series of earth-shattering thoughts. But that, my friend, is a tale for the next leg of our journey. For now, just marinate in this incredible shift, from hard mechanical particles to ripples in an unseen cosmos. It just goes to show that even the ideas of the greatest geniuses must eventually yield to the gentle, persistent pressure of evidence. So there we were. The scientific community, after a century of following Newton's lead, had done a complete about-face. The evidence from Young, Fresnel, and others was just too compelling to ignore. Light was a wave. It was settled. But as so often happens in science, answering one big question just leads to another, even bigger and more puzzling one. And this new question was a real head-scratcher. If light is a wave, what in the blazes is it actually waving in? Think about it. Every wave we're familiar with in our everyday lives is a disturbance in some kind of stuff. You clap your hands, you push the air molecules together, and that compression wave travels through the air to someone's ear as sound. You drop a pebble in a pond, and the water molecules bob up and down, passing that energy along to the shore. The wave isn't a thing itself. It's a state of the thing. It's a pattern of energy moving through a medium. So, light waves traveling effortlessly across the mind-boggling emptiness of space from the sun to the earth must also have a medium, right? There had to be some kind of cosmic stuff filling that void. This was the resurrected idea of the luminiferous ether. It wasn't just a wild guess anymore. It became a necessary foundational assumption. For the wave theory of light to hold, the ether had to exist. Now, this wasn't some vague mystical concept. 19th century physicists were brilliant mechanists. They set about defining the properties this ether must have with meticulous, almost comical precision. It had to be utterly frictionless, because the planets and stars had been sailing through it for billions of years without slowing down a whit. If it had any viscosity at all cosmic motion would have grinded to a halt eons ago. At the same time, it had to be incredibly, unthinkably rigid and elastic. Why? Because light waves oscillate at terrifyingly high frequencies. We're talking hundreds of trillions of times per second for visible light. To support vibrations that rapid, the medium can't be a wobbly jelly. It has to be stiffer than the hardest steel imaginable. So, picture this substance. It must be a solid more rigid than diamond to vibrate that fast. Yet it must be more insubstantial than the faintest whisper to allow planets to pass through it without resistance. It had to permeate everything, the air, water, glass, and even our own bodies, without us ever noticing it. It was a ghostly, paradoxical substance, but the entire elegant structure of wave optics was built upon it. The ether was the universe's ultimate stage, and everything else was just actors moving upon it. This was the state of play for much of the 1800s. Physics was confident, proud, and felt it was on the verge of having everything figured out. The laws of motion, gravity, thermodynamics, and now optics were all falling into place. It was in this atmosphere of near completion that a quiet, unassuming Scottish physicist named James Clerk Maxwell entered the scene. Maxwell was a genius of a different sort. Where Newton was a titanic force of nature, deriving laws through immense intellectual power, Maxwell was more like a cosmic composer, hearing the hidden harmonies of the universe and writing down the score. His project was one of breathtaking ambition: to tidy up the entire, somewhat messy, field of electricity and magnetism. By his time, a lot of the pieces of the puzzle were already on the table, discovered through brilliant experimental work. People like Michael Faraday had done incredible things. Faraday, who had little formal mathematics, thought in terms of intuitive physical concepts. He imagined invisible lines of force spreading out from magnets and electric charges. He discovered electromagnetic induction, that a changing magnetic field could create an electric current in a wire, which is the fundamental principle behind the electric generator that powers our world. But these were largely separate discoveries, a collection of rules and laws. What Maxwell did was pure magic. He took all these disparate pieces, the laws of how electric charges attract and repel, how currents create magnetic fields, how moving magnets create currents, and he wove them together into a single, unified, and mathematically gorgeous tapestry. He distilled everything into 4 compact symmetrical equations. Today, we know them simply as Maxwell's equations. If you ever meet a physicist and they get a misty, faraway look in their eyes when they mention these equations, you'll understand why. They are considered one of the most beautiful and profound achievements of the human mind. Now, I promised plain language, so I won't tell you the equations. But let's try to feel what they say. Imagine the electric and magnetic fields. Don't think of them as complicated math. Think of them as an invisible landscape. An electric charge, like an electron, creates a kind of slope in the electric field around it, a hill or a valley. Other charges feel this slope and roll downhill, which is why they attract or repel. A moving electric charge, an electric current, creates a little whirlpool in the magnetic field. That's why a wire with current flowing through it can deflect a compass needle. Maxwell's equations are like the rule book for how this invisible landscape behaves. They tell you how a hill in the electric field here will create a whirlpool in the magnetic field over there. And crucially, one of them, a little mathematical twist that Maxwell added to the known laws, said something new. A changing whirlpool in the magnetic field could, in turn, create a slope in the electric field. Do you feel the loop closing? It's a feedback loop. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This is where Maxwell had his stroke of genius. He realized this loop could become self-sustaining. Imagine you give a single brief shake to the electric field at one point. That shake creates a changing electric field, which instantly creates a magnetic field right next to it. But that magnetic field is brand new, so it's changing as it pops into existence. And that changing magnetic field, according to the rule book, must now create a new electric field a little further out. And that new electric field is changing, so it creates a new magnetic field even further out. And on it goes. The initial shake sends a ripple cascading through the intertwined electric and magnetic fields. The disturbance doesn't just fade away. It propagates. It becomes a wave, an electromagnetic wave. He had discovered, purely from the mathematics on his page, that waves of electricity and magnetism must exist. They weren't just a possibility. They were a direct consequence of the laws of nature. It was a staggering prediction. But then he asked the next obvious question. How fast would this wave travel? He took his equations and calculated the speed of this self-propagating disturbance. The number popped out from a combination of two fundamental constants, one that measured how responsive the electric field is to charge, the permittivity of free space, and one that measured how responsive the magnetic field is to current, the permeability of free space. When he crunched the numbers, the result was approximately 300,000 kilometers per second, 209,792,458 meters per second, to be precise. And his jaw must have hit the floor. This number was already famous. It was the speed of light, measured by astronomers and experimenters like Hippolyte Fizeau and Léon Foucault. It was just a number you could look up in a book. And here it was, emerging from the pure abstract mathematics of electricity and magnetism. It couldn't be a coincidence. This was the monumental revelation. Light wasn't some separate, unique phenomenon. It wasn't a weird vibration in a mysterious ether. It was an electromagnetic wave. That shake you give to the electric field to start the wave, that's what an atom does when an electron inside it jumps from a high energy level to a low one. It shakes off the extra energy as a little packet of electromagnetic wave. What we perceive as visible light, the reds, blues, and violets, are just electromagnetic waves with a very specific range of wavelengths, a tiny slice of a much grander pie. Maxwell's equations revealed that this electromagnetic spectrum was vast. If you shook the field more slowly, you'd get waves with longer wavelengths. These would be radio waves and microwaves. If you shook it much, much faster, you'd get waves with incredibly short wavelengths. Ultraviolet light, X-rays, gamma rays. They are all the same fundamental thing, traveling ripples in the electromagnetic field, all governed by Maxwell's rules, all traveling at that same unwavering speed, c. This was a unification of cosmic proportions. The force that makes a balloon stick to your hair after you rub it, static electricity, and the force that makes a compass point north, magnetism. And the light that allows you to read this sentence were all now revealed to be different manifestations of a single underlying force, electromagnetism. It was a breathtaking simplification of the cosmos. But here's the funny thing. In solving one mystery, the nature of light, Maxwell had inadvertently made the other mystery, the ether, even more acute and awkward. Because now, this electromagnetic wave wasn't just a vibration in the ether. According to his math, it was a vibration of the electric and magnetic fields themselves. So, what was the ether now? Was it the field, or was the field a property of the ether? The stage was becoming confused with the actors. The need to detect this ether, to prove its existence once and for all, became the most pressing mission in all of physics. They had to find this ocean they were all swimming in. And this desperate, ultimately futile search would set the scene for the greatest upheaval in physics since Newton, an upheaval we now call relativity. But that, as they say, is a story for another time. For now, just sit with the awe of Maxwell's accomplishment. With nothing but pen, paper, and the power of thought, he predicted the entire electromagnetic spectrum and revealed the true, unified nature of light. So, Maxwell's equations gave us this speed, c, as a fundamental constant of nature. But a nagging question remained. A constant relative to what? If light is a wave in the ether, like sound is a wave in air, then its speed should be measured relative to that ether. If you are moving through the ether, The speed of light you measure should be different. Imagine you're standing still on a windless day and you clap your hands. The sound waves travel away from you at about 343 meters per second in all directions. Now, imagine you're in a car moving at 30 meters per second and you honk the horn. The sound waves traveling forward from your car would be going 343 plus 30, 373 meters per second relative to the ground. The waves traveling backwards would be going 343, 30 or 313 meters per second relative to the ground. The speed of the wave depends on your motion relative to the medium, the air. Physicists in the late 19th century were absolutely convinced the same must be true for light and the ether. So, they devised incredibly clever and sensitive experiments to detect our motion through this cosmic ether. The most famous of these was the Michelson-Morley experiment in 1887. The idea was brilliant. The Earth is orbiting the Sun at about 30 kilometers per second. So, at various points in its orbit, it should be moving through the ether at different speeds and in different directions. This ether wind should affect the speed of light. Albert Michelson and Edward Morley built a device called an interferometer that could split a beam of light, send the two parts on paths perpendicular to each other, and then bring them back together. If the speed of light was different in different directions due to the ether wind, the two beams would be out of phase when they recombined, creating an interference pattern. They could then rotate their apparatus, and the pattern should shift. They performed the experiment with painstaking precision. The result was earth-shattering. Nothing. No shift. No interference pattern change. It was as if the ether wind didn't exist. The speed of light was measured to be exactly the same in every direction, regardless of the Earth's motion. This was a paradox that completely baffled the physics community. It was like honking your car horn and finding that the sound waves always travel away from you at 343 ms, whether you're parked or speeding down the highway. It made no sense within the existing framework of physics. They tried every conceivable explanation. Maybe the ether was dragged along by the Earth. Maybe the experimental apparatus itself contracted in length in just the right way to hide the effect, an idea proposed by George Fitzgerald and Hendrik Lorentz. These were patches, and they felt like patches. The foundation of physics was creaking. The stage was set for a revolution. So picture the scene. It's the dawn of the 20th century. Physics is in a state of quiet crisis. On the surface, everything looks magnificent. The great edifice of classical physics, built by Newton, solidified by others, and crowned by Maxwell, seems complete. But those inside the house know about the cracks in the foundation. The biggest crack of all is this luminiferous ether. They've built this beautiful, elaborate theory that depends entirely on its existence. And yet, despite their most heroic efforts, no one can find it. The Michelson-Morley experiment, and others like it, have all come up empty. It's like the entire scientific community is throwing the most elaborate party for a guest of honor who simply never shows up. The table is set, the champagne is chilled, and the chair remains empty. The silence is getting awkward. Some of the greatest minds of the era are trying to patch the cracks. Brilliant people like Hendrik Lorentz and Henri Poincaré are tinkering with the equations, trying to find a way to explain why the ether wind can't be detected. They come up with ingenious ideas, like the notion that objects actually physically contract in their direction of motion through the ether, a concept called Lorentz contraction. Their math is actually getting very close to the answer, but it's still a kind of mathematical fudge. It's a fix, a way to save the beloved ether theory, to explain away the null result. It's as if they're saying, well, the guest of honor is here, he's just become miraculously and conveniently invisible at the last second. Into this scene of polite, frustrated confusion walks a young man who is, in many ways, an outsider. He's not a professor at a prestigious university. He doesn't have a lab. He's working in the Swiss patent office in Bern, a day job he took because he couldn't get an academic position. His name is Albert Einstein, and his great power in this moment isn't his mathematical skill, though it was formidable, but his profound physical intuition and his sheer intellectual courage. He looked at the same problem everyone else was looking at, but he asked a different, more fundamental question. Everyone was asking, how can we save the ether theory? How can we explain why we can't detect it? Einstein, in a move of breathtaking boldness, asked, what if we just get rid of it? What if the ether doesn't exist at all? What if we stop trying to force light to behave like every other wave and accept it on its own terms? His starting point wasn't the failed experiment. It was the beautiful, immutable laws of James Clerk Maxwell. He was utterly captivated by them. He saw in them a truth that was more fundamental than the intuitive, everyday physics of Galileo and Newton. And he began to play with a thought experiment, a favorite tool of his. He asked himself to imagine chasing a beam of light. Let's try to do that with him. Imagine you're on a superpowered cosmic skateboard and you accelerate until you're matching the speed of a light wave, riding right alongside it. Now, according to the old Newtonian way of thinking, what should you see? Well, if you were riding alongside a sound wave, you'd see the wave of compressed air just hanging there, static, not moving relative to you. If you were riding alongside a water wave, you'd see the peak of the wave, frozen in place. So, by that logic, if you ride alongside a light wave, you should see a frozen, oscillating electromagnetic field. A static pattern of electric and magnetic energy, just hanging in space, not going anywhere. But Einstein, who knew Maxwell's equations inside and out, immediately realized this was nonsense. A stationary oscillating electromagnetic field is an impossibility. It's like saying you can have a wave in the ocean that is moving. It's going up and down, but also not moving. It's not traveling towards the shore. Maxwell's equations simply do not permit a solution for a frozen wave of light. The equations demand that electromagnetic waves propagate. They must move, and they must move at one speed and one speed only. The speed c, the constant that fell out of the math. A stationary light wave would violate the very laws that define what light is. This was the paradox. Classical physics said one thing, and Maxwell's equations said another. So who was right? Einstein's genius was to trust the equations. He concluded that it must be impossible to catch up to a beam of light. No matter how fast you go, no matter how powerful your cosmic skateboard is, that beam of light will always race away from you at exactly 299,792,458 meters per second. You will never, ever see it as a stationary wave. Its speed relative to you is always c, always. Now, let that sink in for a moment. This is where it gets really weird, and where Einstein parted ways with all of classical intuition. Think about throwing a baseball. If you throw it at 50 miles per hour from a car moving at 50 miles per hour, someone standing on the roadside will see the ball moving at 100 miles per hour. Velocities add up. But if you turn on a flashlight on that same car, the light does not fly out at c plus 50 miles per hour. It flies out at exactly c. And if the car was going at 99.99999% the speed of light and you turned on the headlights, the light from those headlights would still race away from the car at exactly c, not at c, plus a little bit. And someone standing on the roadside would also measure that same light beam to be moving at exactly c. It defies all common sense, but Einstein proposed that this is just how the universe works. The speed of light in a vacuum is the ultimate constant. It is the same for everyone, regardless of their own state of motion. It is the one fixed rule in the cosmic game. But how can this be? How can two observers, moving at different speeds, both measure the exact same speed for the same beam of light? The only way this is logically possible is if something else we consider absolute and fixed is actually not fixed at all. That something is time and space themselves. To make this work, Einstein needed a foundation. He built his new theory on two simple but revolutionary postulates. The first was an old idea, made new. It's called the principle of relativity. Galileo had articulated it centuries before. It simply says that the laws of physics are the same for all observers who are moving at a constant velocity relative to each other. If you're in a smoothly moving car with the windows covered, no experiment you can do inside that car, rolling a ball, bouncing a spring, measuring the speed of light, can tell you whether you're moving or standing still. There is no such thing as absolute motion. All motion is relative. This was already accepted. Einstein's second postulate was the bombshell. He stated that the speed of light in a vacuum is constant. It is the same for all observers, independent of the motion of the light source or the observer. This was the radical part. He took the null result of the Michelson-Morley experiment not as a problem to be solved, but as a fundamental fact of nature. He elevated it to a law. By combining these two postulates, the relativity of motion and the absoluteness of light's speed, Einstein was forced to conclude that time and space could not be the rigid, unchanging stage that Newton imagined. They had to be flexible. They had to bend and stretch to keep the speed of light constant for everyone. It was the only way to resolve the paradox. Think of it like this. Speed is a measure of distance traveled over time taken. If the speed of light is fixed, but two observers are moving, and both must get that same fixed number, then their measurements of distance and time must be different. The universe, to preserve the sacred constant c, will adjust the very fabric of reality for moving observers. It will slow down their clocks and contract their rulers along the direction of motion. This isn't an illusion or a trick of perception. It is a real, physical effect. Time itself literally passes slower for someone who is moving relative to you. And lengths literally get shorter. This was the heart of the special theory of relativity, published in his 1905 paper on the electrodynamics of moving bodies. It was a theory that didn't try to patch the old system. It completely dismantled it and rebuilt our understanding of the universe from the ground up, with the constant speed of light as its central, immovable pillar. He didn't just explain the failed ether experiment. He made the ether completely irrelevant. There was no need for it anymore. The electromagnetic field wasn't a state of some mysterious medium. It was a fundamental entity in its own right, and its waves traveled at a speed that was built into the very geometry of the cosmos. But how can this be? How can two people moving relative to each other both measure the same beam of light to be moving at the same speed? The only way this is possible is if something else gives. And that something else is our most fundamental concepts, space and time themselves. Einstein realized that for the speed of light to remain constant for everyone, space and time cannot be absolute and fixed, as Newton had believed. They must be flexible and relative. They must stretch and warp to keep the speed of light constant. This leads to two incredible consequences: time dilation and length contraction. Let's unpack time dilation first. Imagine a simple clock. It's made of two mirrors with a pulse of light bouncing between them. One tick of the clock is the time it takes for the light to go from the bottom mirror to the top and back again. Now, imagine you are sitting right next to this clock. You see the light pulse go straight up and straight down. The distance it travels is twice the height between the mirrors. Simple. Now, imagine your friend is watching this same clock, but from a spaceship that is zooming past you at a huge fraction of the speed of light. From your friend's perspective, the clock is moving. So, as the light pulse goes from the bottom mirror to the top, the entire clock has moved sideways. Your friend doesn't see the light pulse take a straight up and down path. They see it take a diagonal path, a longer path. But remember the rule: both you and your friend must measure the speed of that light pulse to be exactly c. Speed is distance divided by time. For your friend, the distance the light travels, the diagonal, is longer. For the speed to still come out as c, the time for that journey must also be longer. Your friend sees the clock tick more slowly than you do. Time itself is passing more slowly for the moving clock from your friend's perspective. This isn't an illusion. It's not a trick of perception. Time itself is stretching. If your friend on the spaceship had an identical clock, you would see their clock ticking slowly, and they would see your clock ticking slowly. This is reciprocal. The faster you move through space, the slower you move through time. Your rate of time is relative to your state of motion. This has been experimentally verified countless times. We have ultra-precise atomic clocks. If you fly one around the world on a jet plane, and then compare it to one that stayed on the ground, the one that traveled will be ever so slightly behind. The effect is tiny at human speeds, but it is real. For particles and accelerators moving at 99.99% the speed of light, their internal clocks slow down so much that they live millions of times longer than they would if they were stationary. Moons, particles created in the upper atmosphere by cosmic rays, should decay before they reach the ground. But because they are moving so fast relative to us, their time is dilated, and a significant number of them survive the journey to the surface. Time dilation is a confirmed fact of our universe. Now let's look at length contraction. This is the other side of the coin. To keep the speed of light constant, not only does time have to stretch, but space has to contract. Let's go back to our cosmic highway. You're in your supercar, and you're trying to measure your speed by timing how long it takes to pass between 2-mile markers that are, from the perspective of someone standing on the roadside, exactly 1 mile apart. Now, as you go faster and faster, approaching the speed of light, time dilation is happening for you. Your watch is ticking slower. So, from your perspective, the time it takes for you to go from one marker to the next is very short because your sense of time is stretched out. But speed is distance over time. If the time you measure is very small and the speed of light is fixed, then the distance between those two markers must also become smaller to make the math work. From your perspective, the mile markers are squeezed together. The entire universe is contracting along your direction of motion. A journey to a star that is 100 light years away from Earth might, from the perspective of an astronaut traveling at 99.9% the speed of light, only be a few light years long. The distance itself shrinks. Again, this is not an illusion. It is a real physical contraction of space. So, we have time dilation and length contraction. These are the mechanisms the universe uses to protect the sanctity of the speed of light. The faster you go, the more time slows down for you, and the more the universe in front of you squashes up. So, we've just watched Albert Einstein, in one breathtaking paper, completely redefine our understanding of space and time. He's shown us that the universe has a single, unwavering speed limit, the speed of light, and that the very fabric of reality warps itself to protect it. But 1905 was what we call his miracle year for a reason. He wasn't done. Just a few months later, he published a short 3-page addendum to his theory of relativity. It wasn't flashy. It didn't have a dramatic title, but it contained a single tiny equation that would become perhaps the most famous string of symbols in all of human history. E equals mc squared. It's so ubiquitous now that we see it on t-shirts and in cartoons, but its true meaning is often lost. We know it has something to do with atomic bombs and nuclear energy, but its profundity goes so much deeper than that. It is the final, crucial piece of the puzzle that explains, once and for all, why you and I and every material thing in the universe are forever bound to travel slower than light. To understand it, we have to go back to what we thought we knew. In the old Newtonian world, mass and energy were two completely separate things. Mass was just stuff, the amount of matter in an object. It was measured in kilograms and was thought to be constant and unchanging. Energy was what that stuff could do. It was the capacity to do work, to move things, to cause change. They lived in different boxes. You could convert one form of energy to another, like the chemical energy in gasoline being converted to the kinetic energy of a moving car, but you could never convert energy into mass or mass into energy. That was unthinkable. Mass was the permanent, indestructible stuff of the universe. Einstein's equation blew that idea to smithereens. That little equals sign in the middle is the most important part. E equals mc squared. It means energy and mass are not just related, they are equivalent. They are two different forms of the same fundamental thing. Mass is simply concentrated energy. And energy has a mass-like quality. They are interchangeable, like different currencies, and the exchange rate is the speed of light squared. Now let's talk about that exchange rate, because it's the key to everything. The speed of light, c, is a huge number, 300,000 meters per second. But we're not multiplying by c, we're multiplying by c squared. That's 300,000 times 300,000. That's 90,000, 90 quadrillion. That is an almost unimaginably gigantic number. What this means is that a tiny, tiny amount of mass is equivalent to a truly colossal amount of energy. Think of it like this. Imagine you have a single paperclip. It weighs about 1 gram. If you could somehow convert every single atom in that one paperclip entirely into pure energy, unleashing the full force of E or mc2, how much energy would you get? The answer is enough to power a medium-sized city for an entire day, enough to rival a small nuclear bomb. All of that potential, locked away inside the invisible structure of a paperclip. It's utterly mind-boggling. This is why nuclear power is so potent. In a nuclear reactor, we're not converting mass to energy completely. We're just nibbling at the tiniest edges of atomic nuclei, causing a mass loss that is almost imperceptibly small. But because of that monstrous c-square multiplier, Even that tiny loss of mass unleashes a staggering amount of energy. But for our story about the cosmic speed limit, the most important implication of E equals mc squared is a bit more subtle. It tells us that energy has mass. Not just that mass contains energy, but that energy itself has a kind of heaviness to it. If you take an object and you add energy to it, say you heat it up, you are actually making it ever so slightly more massive. The kinetic energy of its jiggling atoms contributes to its total mass. It's an immeasurably small effect for a hot cup of coffee, but it's real. Now let's apply this to our cosmic joyrider. You, in your supercar, foot slammed on the accelerator, trying to reach the speed of light. As you go faster and faster, you are gaining kinetic energy, the energy of motion. In the old Newtonian world, this was a simple, linear relationship. To double your speed, you needed to quadruple your energy, but it was always a finite amount. You could always, in theory, add a little more energy to get a little more speed, all the way up to infinity. But Einstein's universe is different. Because of E equals mc squared, that kinetic energy you're pouring into your car doesn't just make it go faster. It actually adds to the car's mass. The faster you go, the more kinetic energy you have, and therefore, the more massive you become. Think about that. You're not just feeling heavier from the G-forces. Your actual physical inertial mass, your resistance to acceleration, is literally increasing. So you're caught in a vicious cosmic cycle. You press the accelerator to go faster. You pour energy into the car. That energy makes the car more massive. The more massive the car becomes, the harder it is to accelerate it further. Remember Newton's second law. It takes more force to accelerate a more massive object. So, to get the same amount of acceleration you got before, you now need to pour in even more energy. But that new energy makes the car even more massive, which makes it even harder to accelerate, requiring even more energy. It's a feedback loop from heaven or hell, depending on your point of view. The closer you get to the speed of light, the more pronounced this effect becomes. Your mass begins to skyrocket. At 90% the speed of light, your mass isn't just a little bit more, it's more than double your rest mass. At 99% the speed of light, your mass is about 7 times greater. At 99% the speed of light, your mass is thousands of times greater. Now, imagine the final push to actually, truly reach the magic number of 100% the speed of light. The math of Einstein's equations gives us a terrifying result. Your mass would become infinite, and to accelerate an object of infinite mass, you would need an infinite amount of energy. And infinite isn't just a big number. It's not something you can find by building a bigger engine or a more powerful fuel. There is not an infinite amount of energy in the entire observable universe. It simply does not exist. And this is the ultimate physical reason why you cannot go faster than light. It's not that there's a police barricade across space-time. It's not that your engine isn't good enough. It's that the very act of trying to get there makes you infinitely heavy and demands an infinite price. The universe has a built-in physics tax that rises exponentially the closer you get to the limit, and the final payment is impossible. The speed of light isn't a barrier, it's a horizon. You can approach it, but you can never cross it. This is the beautiful, final synergy between Einstein's two 1905 revelations. Special relativity establishes the universal speed limit, and E equals mc squared provides the physical mechanism that enforces it. The constant c isn't just the speed of light. It's built into the very exchange rate between mass and energy. It is the fundamental conversion factor of the universe, and it ensures that the cosmic speed limit is not just a suggestion, but an unbreakable law of reality for anything that has the misfortune, or the fortune, to weigh more than nothing. Only massless particles can travel at the speed of light. And what are the massless particles we know? The photon, which is the particle of light, and the gluon, which carries the strong nuclear force, and, importantly, gravitational waves, ripples in spacetime itself, also travel at c. For these entities, time and space behave in the most extreme ways. From the perspective of a photon, its journey is instantaneous. Because of time dilation, time does not pass for a photon. From the moment it is emitted to the moment it is absorbed, no time elapses in its own frame of reference. Also, because of length contraction, the entire universe is contracted to a point in the direction of its travel. The photon experiences no distance. It is everywhere along its path at once. This is the universe's ultimate loophole for its own rule. If you have no mass, you must travel at c, and you do not experience space or time. It's a truly alien existence. This leads us to the concept of causality, which is perhaps the most important reason why the speed of light limit exists. Causality is the law of cause and effect. It is the fundamental principle that the cause must happen before the effect. This is the backbone of reality, of logic itself. If you could travel faster than light, you could break causality. You could create paradoxes. Imagine you have a super-fast spaceship that can go twice the speed of light. You fly away from Earth to a planet 10 light years away. From Earth, they see you leave. You get in your ship and zip over to the planet at 2c. So the trip only takes you 5 years from your perspective, though due to time dilation, it would be less for you. You arrive and immediately send a message back to Earth using a super-fast radio wave, which, like all light, travels at c. The message says, "I arrived safely." Now let's track the timing from Earth's perspective. You left Earth at year 0. The light of your departure also travels out at c. It takes 10 years for that light to reach the distant planet. But you, traveling at 2c, get there in 5 years. You send your message at year 5, Earth time. That message travels back at c, taking another 10 years to get to Earth. So, Earth gets your "I arrived safely" message at year 15. But here's the paradox. Someone on Earth at year 6 looks at the distant planet with a powerful telescope. The light arriving at their eye at year 6 left the planet 4 years ago. Because it's 10 light years away, light from year 2 is arriving at year 12 and so on. So at year 6, they are seeing what happened on the planet at year 4, 4 years before you even left Earth. They see an empty landing pad. Now you actually send your message from the planet at year 5, Earth time. That message is an event. The light from that event, you standing on the platform sending the message, will travel to Earth, taking 10 years, arriving at year 15. But because you can travel faster than light, you have created a situation where the effect, the message arriving at Earth at year 15, could in principle be used to send a message back to yourself before you left. It gets incredibly messy, and it allows for scenarios where you could prevent your own departure, creating a grandfather paradox. The universe, to protect causality and prevent such logical nightmares, imposes a universal speed limit on any transfer of information or matter. The speed of light is the speed of causality. It is the maximum speed at which any influence, any signal, any cause can propagate through the universe to create an effect. This is the deepest reason of all. The universe is built on a foundation of cause and effect, and that foundation would crumble if anything could outrace a light beam. We've talked about particles with mass, which can't reach C, and massless particles, which must travel at sea. But what about things that seem to go faster? There are a few fascinating apparent exceptions that actually prove the rule. One is the expansion of the universe itself. Distant galaxies are moving away from us due to the expansion of space. The further away a galaxy is, the faster it appears to be receding. For galaxies beyond a certain point, their recession velocity is greater than the speed of light. Is this breaking the rule? No, absolutely not. Because they are not moving through space faster than light. Instead, the space between us and them is itself stretching. The galaxy is locally at rest in its own patch of space. There is no violation of causality here because no information, no signal is being sent from that galaxy to us at superluminal speed. The light it emits towards us is still traveling through space at speed c, but the space it's traveling through is expanding, making the journey immensely long. This is a key distinction. Motion through space is limited to c. The expansion of space itself is not. Another interesting phenomenon is quantum entanglement, often called spooky action at a distance by Einstein. You can create two particles that are intrinsically linked or entangled. Measuring the property of one, say its spin, instantly determines the property of the other, no matter how far apart they are. This seems like instant communication faster than light. But again, physicists have carefully studied this, and it turns out you cannot use this to send any meaningful information. The correlation between the particles is instant, but it is random. You can't force one particle into a specific state to send a Morse code message to the other side. The person measuring the second particle just sees a random result. It's only when they compare their results with the first person later, using a slower than light communication channel, that they see the spooky correlation. So, no information, no causality-breaking signal is transmitted faster than light. There are also theoretical constructs like tachyons, which are hypothetical particles that always travel faster than light. They are a mathematical possibility in some equations, but they come with a host of problems, like potentially having imaginary mass in the mathematical sense, and, you guessed it, causing causality violations. There is not a shred of experimental evidence that they exist, and most physicists believe they do not, precisely because they would break the fundamental causal structure of the universe. So, where does this leave our cosmic joyrider? You're in your car, pedal to the metal. You're pouring unimaginable amounts of energy into acceleration. But with every iota of speed you gain, your mass increases, making further acceleration harder. Time outside is screaming past, but for you, it's slowing to a crawl. The stars ahead are turning blue-shifted, their light compressed into higher energies. The universe ahead is contracting into a dazzling, thin disk. The energy required to go even a fraction of a percent faster is becoming greater than the total energy output of stars. To reach C itself would require infinite energy. You are not being stopped by a barrier. You are being stopped by the very nature of mass, energy, space, and time. The universe is not saying no, it's saying the price is infinite. And in a finite universe, that's the same thing. The speed of light is more than just a number. It is a fundamental constant, a conversion factor between space and time, woven into the fabric of spacetime itself. It is the ultimate arbiter of reality, the guardian of cause and effect, the thread that holds the cosmic tapestry together. It tells us that the universe is not a static, rigid stage, but a dynamic, flexible, and deeply interconnected whole where space and time are relative and malleable. The fact that we can't go faster than light is not a limitation of our engineering. It is a limitation of reality itself. It is a signature of a universe that has a deep, logical structure, one that ensures that tomorrow follows today, that effects follow causes, and that the story of the cosmos makes sense. So the next time you flip a switch and a room is instantly filled with light, remember the incredible journey of those photons. They travel at the ultimate speed, not because they are powerful, but because they are weightless. They are the universe's purest messengers, and they obey its most fundamental law, that nothing can overtake them in the race to define what happens next. And in that simple, unwavering constancy, we find the very framework that allows for a stable, understandable, and beautiful universe to exist at all. And so, as that beam of light continues on its endless journey, forever constant, forever unwavering, we slowly bring our own minds back from the edges of the cosmos, back to the comfort of the here and now. I hope this journey through space and time has brought a sense of wonder and calm to your evening. If this peaceful exploration helped you unwind or gave your mind something gentle to focus on, I'd be so grateful if you'd consider subscribing to Hafee Sleep. It's the easiest way to make sure our next journey finds you right when you need it. And if you enjoyed it, pressing that like button lets me know which topics bring you the most comfort. But most of all, I'd love to hear from you. Leave a comment and let me know. Where are you listening from, and what time is it there? It's such a beautiful thought, all of us connected by curiosity and calm from every corner of the world. Thank you for sharing this time and space with me. Until next time, be kind to your mind, gentle with your thoughts, and remember to rest deeply. Good night, dear dreamers.